Okay, so let's start our week 6. Yeah. So this is basically after this lecture today we are half distance, right? Okay, so what I am planning to do with you today is Spar theory, and diagonal tension fields. Okay? So that is the program for today. So I will introduce you to this theory, and then we'll do one or two examples, which are not difficult at all. You are going to see this is a quite simple and interesting subject, and then we go home. Okay? I know that you are we go home, but that should be very close to 6. Yeah, close to 6. We don't go home now. Yeah, but I know that you guys are really rushing with your project proposals, right? Yeah, I know that. So maybe I will try to see if we can finish a bit earlier. I know you have meetings that were postponed for 6 p.m. today. Yeah? Yeah? You too? And then, maybe we can finish a bit earlier for you to... Deadline is tomorrow, right? For the proposal. It's tomorrow, right? Or it's today? It's tomorrow, right? Yeah. Okay. All right, so we are going to be looking at in the wing, you will have the spar, which basically is a big beam, right? Well, in some wings you can have more than one spar. Well, which in some wings, in most of them, you have two spars, or some wings have 3 spars. Yeah? So something like this, which is basically inside of, this is the skin of your wing. So inside, of course, this spar looks too big here, right, in this wing. But you have these kind of things, and then you connect the spar to the skin. You bond these two with rivets, for example. Yeah. And basically this big beam that you have running longitudinally along the wing is going to be responsible for carrying the major load, the lift, right? Yeah. So basically the skin is just to give the aerodynamic shape for generation of lift, but that lift is then transferred to this spar through stiffeners, posts, ribs. Yeah, they transfer the load from the skin to the spar, and it is this spar, this big beam, that is going to carry all of the load that you have on the wing. Okay. So I'm going to now basically not be drawing all this wing every time in 3D. So we are going to be representing this spar like if it is a cantilever beam, yeah, where you will have some components that we need to identify here. So you will have this top and bottom flanges. Okay. So we can say this is upper flange. If you are doing idealized structures, if you idealize this beam or this spar, you can also say this is the upper boom. You will put a boom there, right? This will be the lower flange. boom, yeah. These guys will be the stiffeners, right? Okay. And of course you have what you have between these two stiffeners is basically a plate or a web, right? And these different components you have here in the spar, they will be responsible for carrying different types of stresses, of loads, okay? Yeah? So for example, the webs, they will carry shear stresses. The stiffeners and the flanges, they will carry direct stresses, yeah? Okay, so these are the main components. So we can say that for example, if I continue here, for example, if I do a section here, a cutting section, okay, a cutting section here on my you will have these flanges carrying these forces, force in the upper flange, force in the lower flange. So you can say that these forces are going to be equal to the bending moment in this section divided by the height h, which basically is this dimension, right? So for example, if you do the equilibrium summation of moments about this point, for example, you can easily get, so don't forget you will have here the bending moment, right? M. You can easily get this equation, right? So you can obtain the forces in the flanges from the bending moment that you learned in year 1. Remember when we did bending moment diagrams? Divided by the height of this web, okay? So these flanges, they will carry this kind of axial or longitudinal loads. Now the web, so this is the web, I forgot to put the B there. You know also that from year 1 we did the bending moment diagrams and the transverse shear force diagrams, remember? Yeah? So you will have also a transverse shear force. I think we call it V, right? This transverse shear force V. So because of this transverse shear force V, we can say that the web will be carrying a shear flow, which is going to be equal to this transverse shear force over the height of the web again, right? So don't forget that shear flow is always a force per unit length. Yeah? That's why you are dividing here the force per the height of the web, so you get the shear flow in that web. Okay? Now, these stiffeners that you have here in the middle, these stiffeners or posts, we also call these posts. Yeah? These ones I'm putting here in green. They have basically two major functions. One is to transfer the load, the lift, to transfer between the flanges and the webs, to transfer that load. The second function is, which is a very important function, is to reduce the width of these webs, so this width, and to control the buckling. Okay? We are not going to develop buckling here, we don't have time, but for example, the buckling of a plate is strongly dependent on the width and height of the plate, okay? So if you have a very large width, the buckling can happen for much lower forces, So by putting these stiffeners here, basically we are reducing the width of the plates so that we can control the buckling better. So these are the two major functions of the stiffeners, okay? Yeah. So this is a very quick overview of the major components you have in these spars: the flanges, the stiffeners, and the web, which basically are plates, okay? And the thing is, as everything in aircraft, we always want to design a lightweight, structure in aircraft. So we want for example, the thickness of these webs. So this web, for example, we want the thickness to be as small as possible. Okay? But if this thickness becomes so there are two different ways you can design these webs. One is what we call the thick web. Yeah, just a moment, let me just finish it. What we call thick web is that, okay, you have this shear flow. Yeah, so if you want to get the shear stress, you just need to divide this shear flow, which is this. You need to divide by the thickness, of the web, of this plate. Then you get the shear stress. And if this thickness is large enough, the design criterion is for example, if you use, for example, the Tresca yield criterion, right? You need to compare the stress you get installed on the web due to the load needs to be lower than the maximum stress the material can carry, right, at yielding point, right? Of course, you can affect this with a factor of safety, yeah. And then we design for a thick web. We design this for yielding, basically, right? Now, in aircraft, because we're trying always to reduce weight, we design these webs not for yielding, but for buckling, yeah. And that's when we say that we are using a thin web, okay, for the spar. So basically, we will allow buckling to happen, but in a controlled way. And that's what I want to show you next, what is going to happen. And the best way I found to show you that is to give you an analogy. So I'm going to try to represent that analogy here. Look at this. Imagine you have this plate, okay? But we are going to replace this plate with two struts like this, okay? So we will say this is going to be strut A, while this is going to be strut B, for example, okay? And then we are going to apply a force, a transverse shear force V at this point, okay? So what is going to happen after I apply this force, and I'm going to exaggerate a bit here for visualization. This is going to deform something like this, right? Yeah? So basically this strut A. So you will have your force V here, yeah? Basically your strut A under these deformed conditions is going to be in compression, yeah? While the strut B is going to be in tension. Yeah, you can imagine this, right? So when you deform these two struts, strut A, basically the final length of strut A will be smaller than the initial length, so it means it is going to be compressed. And strut B, the final length, so if you want this length here, is going to be higher than the initial length, this one, right? Yeah. So it means strut B was stretched, right? So basically strut B is going to be in tension, while strut A is going to be in compression, yeah? And what is going to happen is, if we are working with a thin web in our spar, and if we assume that this strut A is the slenderness ratio is very high, so it means under this compressive force in strut A, it is going to buckle, okay? So what is going to happen after it buckles is this, so I can draw a third one here below. what is going to happen is that this plate is going to have only this strut B in tension, carrying the load, yeah? Because once the strut A, this strut buckles, once it buckles, it means it cannot carry the load anymore, yeah? So it's gone, okay? So, and basically what is going to happen is this plate or this web is going to be carrying this load V only in tension, yeah? Because the compressive part, because it buckled in that direction, is not there anymore. So that's why we call these diagonal tension fields. Basically, the load now is being carried in the diagonal direction. Yeah, you can see from this analogy very well, right? So, did you understand this analogy more or less? What's going to happen? So basically, you have these two struts. One will be in compression. The other one will be in tension. The strut in compression will buckle, and then after that happens, it is not able to carry load anymore. It's gone. So all this load V that you have here is going to be carried by this strut B in tension. Yeah? So keep this in mind, because we are going to see now the analogy on our spar. What is going to happen there. And that's what I want to focus now with you. So we will have now ours. So let's concentrate on imagine you have, for example, a beam with only one web, something like this. Yeah. So you have the flanges here and one stiffener here. So let's concentrate on this web that you have here. So maybe I can write it. I can draw it here in red. Yeah, this web. As I told you, this web is carrying only a shear stress. So if I represent here, well, don't forget you are going to have a transverse shear force V. Yeah, and because of that, you are going to develop in this web a poor shear stress. You remember this from year 2, right? You did this in solid body mechanics, right? Plane stress analysis, yeah? If you have an element only under shear, poor shear, right? You have something like this. So this is the shear stress, tau, yeah? Okay? You remember this, right? So this is what is happening on the web. You have this kind of stress installed on the web. Now, another important concept you need to have from year 2 is Mohr Circle. You are all familiar with that? Mohr Circle? I can see your face. No? You don't like it? You don't like it, yeah, but life is like that. We need, yeah? Mohr Circle is a very important thing because, okay, so let's do a very quick review of the Mohr Circle. We are going to need it here. So how can I represent this stress state into the Mohr Circle? So basically, this is so you know in the Mohr Circle you have this coordinate system where in the horizontal direction you have the direct stresses, right? In the vertical direction you have the shear stresses, yeah? How can I represent the... Let me draw this a bit better. How can I represent this poor shear into the Mohr Circle? Well, it's a circle with the center at the origin of this coordinate axis, okay? Of this referential, okay? So you have this circle here is your Mohr Circle. So remember that this point and this point is where you have your shear stress tau from here, yeah? You know that a point in the circle represents a shear plane, right? So for example, I'm going to draw it here. You have this shear stress, yeah? So now look at this. If you take this shear plane here, this one in green, the stress component you have in this shear plane is this tau stress only. You have a zero direct stress, right? A zero sigma stress. So that's why you have this point here. Look, this point in the circle, it has only a tau component, right? Sigma component is 0, right? If you go now to the other shear plane that you have, this one here, which is perpendicular to the previous one, you also have in this shear plane a shear stress only, right? And that point corresponds to this point here at the bottom. You can see the different colors, right? The green and blue, these 2 points. Why? One is at the top and the other is at the bottom. Yeah, because there is a convention for this. If you put yourself in the center of this element, this stress tends to rotate it anti-clockwise. So anti-clockwise, you plot in the positive tau axis. If you look now at this one, this tends to rotate clockwise. Clockwise, you plot in the negative tau axis. Okay? There's a convention for this. Okay? So, this pure shear stress that you have on the web, this is the Mohr circle you have, and these 2 points are, these points in green, in blue, are the points representing these 2 shear planes perpendicular to each other. So another very important thing is in the Mohr circle is that, for example, these 2 planes here in this picture, they do 90 degrees, right, between each other. Yeah, they are perpendicular. In the Mohr circle, you always represent 2 times this angle. So where is this angle here? Well, these two shear planes, they are represented by these 2 points in green and blue. So the 2 times 90 is this 180 degrees, right? So this angle here, as you can see between these 2 points, is 180 degrees. Is 2 times the 90 degrees before, right? We are going to need this rule as well to make our assumptions. Now, what is another thing we can take here from the Mohr circle? So everything I'm saying about, there's a lot of things I'm not going to speak about Mohr circle, but what I'm saying about Mohr circle is something that you need to use on this Spar theory, okay? Now, another important thing you need is these 2 points that you have here. I'm going to represent them in black. This point and this point. Which points are these? Maximum and minimum direct stresses, right? Which are also known as sigma 1, sigma 2, sigma 3, principal stresses, yeah? So these are the highest. So this is sigma 1, this is sigma 2, sigma 3 is equal to 0. This is plane stress analysis. So this, am I representing this? Because, look at this. This stress state that I have here, which is the one I have in my web, is going to be equivalent. So I will going to write something like this, equivalent to a stress state something like this. This angle is going to be 45 degrees. Okay? And what I will have is let me just see the direction here. Yeah. I will have here, maybe I can use a different color, like sigma 1. And here I will have sigma 2. Okay, so what I'm doing is, I'm looking at these 2 points, this one, sigma 1 and sigma 2, yeah? Look, in the Mohr circle, this sigma 1 and sigma 2, this angle is 180 degrees. So it means here they need to do 90 degrees, which is correct, yeah? 90 degrees, yeah? Another thing, sigma 1 is positive, so it is a tensile stress, stretching. And sigma 2 is negative, it is a compressive stress, yeah? So these 2 stress states, this pure shear and this only represented by the principal stresses, they are equivalent. Why? Because they represent the same Mohr circle. The Mohr circle is exactly the same, isn't it? Yeah? So these two stress states, they are equivalent. And why am I doing this? Well, I'm doing this because what I'm going to do now in the web of my spar, maybe I can draw it here. What I'm going to do is, well, I have my web, right? Flanges and stiffener. What I'm going to do is I'm going to replace this pure shear stress with this one, sigma 1 and sigma 2, because they are equivalent. They are equivalent, right? And why am I doing this? Because you can see now this sigma 2 is a compressive stress, right? And what we are going to do on this web is I'm going to say, okay, I will have here this sigma 2 compressive stress. The web is going to buckle because of this compressive stress, yeah? So you can understand that if I have a plate, if I apply compressive stress, it buckles, right? Yeah? So it's going to buckle in this direction. And then what is going to happen is, after it buckles, my web will be carrying a stress which is going to be only sigma 1 in tension. Because once it buckles under the action of this sigma 2, it will not be able to carry the load in that direction of that compressive stress, right? And then this is when this analogy comes with this example, right? Yeah, same thing, exactly the same thing. We have a compressive stress sigma 2 in that direction, and don't forget from this figure here that this direction of sigma 1 is going to be, so this angle here is going to be 45 degrees. Okay? So, going back to the Mohr circle, what happened to the circle when this buckling happened was that the circle, so I'm going to represent the circle in green now, the circle shifted to the right Yeah? Because this circle here, and particularly this point, which is sigma 1, sigma 2 here equal to 0, right? In this circle, in this green circle, we have these 2 points, which is exactly the stress state that you have here in your web, right? Yeah? You have only a sigma 1, and you have the sigma 2 equal to 0, right? So this is what happened. So after this web buckle in this sigma 2 direction, the Mohr circle basically moved from the origin of the Mohr circle moved from so the center of the Mohr circle moved from the origin of this referential system, so that now the circle is passing on the origin. Okay, this circle in green. So basically, it's translated, right? Okay. So, do you understand this more or less? What happened here? So basically, we are letting this web to buckle in the direction 2, and what we are saying is that the web is going to carry all the load now. So 100% of the load is going to be carried along this 45 degrees direction and in tension. Yes?
We use the translation at the top. It's just a convention that it will be like that. So it will be compressive.
It's not a convention. If you look carefully, that Mohr circle in green represents this basically uniaxial stress state at 45 degrees, right? Sigma 1.
Okay.
Yeah, for example, what I mean is that if I give you something like this, imagine you have this plane stress sigma 1 only this stress, and this sigma 1 makes 45 degrees with the horizontal direction. Yeah? Draw the Mohr circle for this stress. What you have to do is, how do you draw this Mohr circle? Well, first you need to put the axis here, right? You need to start with one shear plane, this one, where you have sigma 1, so you put sigma 1 here. Yeah? Yeah, you have only a direct stress, right? Shear stress is 0, so shear stress tau is 0 in that shear plane. You have only a direct stress in this sigma axis, which is equal to sigma 1, right? So this point here represents this shear plane, right? Now you need to have another point so that you can draw the circle. So where do you get that other point? Well, you get from the other shear plane that you have, which is this one in green. And in this shear plane in green, you have a 0 direct stress and a 0 shear stress. So this point needs to be this one at the origin, right? Once you have these 2 points, the midpoint between these two is the center of the circle, and the circle will have to pass on these 2 points, right? Okay?
Well, so the compression in the other one came from the fact that they were negative. Okay.
Yeah, exactly, yeah. The compression here, is negative, so it represents this point here, right? But what I said after that is, okay, so because of this compressive stress, it will buckle, and then not able to carry the load anymore. Yeah. Yeah. Okay, so this is a very important thing. We need to do something more. So this is getting a bit confusing now. But I need to get at least this. Let me copy this. So this is the direct stress that is being carried in tension with an angle of 45 degrees. So this is also known as a pure diagonal. I can write here is better. This is known as a pure diagonal tension field. This is very suggesting. Look. Poor is because of 45 degrees. There are also incomplete diagonal tension fields where this angle is not really 45 degrees, but is very close to 45 degrees. Okay? So the poor is, this angle is 45 degrees. Diagonal, well, because of this sigma 1 as the diagonal direction of the web, right? Once it is at 45 degrees. Tension, because this stress is in tension. Yeah, so this is very suggestive name for this theory. What we need to do now, before we start solving a practical example, is we need to do a stress transformation. Now, you did stress transformation, right? In year 2, solid body mechanics, transform stresses from one direction to another. Remember that? Not really? Well, I can give you a refresh on that as well. So why do I need to, the first thing is, why do I need to do a stress transformation? Because our goal is going to calculate the forces in the flanges, the forces in the posts or stiffeners, yeah? So we need to transform this stress from this direction of 45 degrees into the horizontal and vertical direction. So basically what I need to do is, I need to transform the stress from here to here, where I want to have, so maybe I can represent now in green, I want to have now the stress components in this direction. So these are the direct stresses, and I also need to have the shear stresses. So these stress components that you have here in green, we need to obtain these stress components in green from this diagonal tension sigma 1 at 45 degrees. So we need to do a stress transformation. And you are going to see later why we need to do this stress transformation, okay? To calculate the forces in the posts, in the flanges, we need all of this. So how do we do this stress transformation? So what I suggest is, let's plot the Mohr circle for this sigma 1 again. So we did it already, so let me just do it here again. So we have sigma axis, tau axis, yeah? We know that this Mohr circle in red needs to pass on the origin, yeah? So this point here is sigma 1. Now, this angle here, 45 degrees, is the angle that we need to use for our stress transformation. In the Mohr circle, we always use 2 times this angle, right? So, look at this. This is the center of my Mohr circle. If I have 45 degrees there, in the Mohr circle I need to have 90 degrees. So, this point here, this angle is 90 degrees, right? Yeah? So this point here and this point here, these 2 points in green in the Mohr circle are going to give me the stress components on these on these 2 shear planes. I'm going to represent here this one in blue and this one in red. Yeah? So maybe I can change the color of those points. So this one in blue is going to be this one here in the bottom. That one in red is going to be this one here at the top. Okay? Now let's start with the one in blue. So, starting with this one in blue, we can, look, the direct stress, if you look at this point and if you look at this referential system sigma tau that we have here for the Mohr circle, the direct stress is the direct stress you measure in this horizontal axis, right? Yeah? Is going to be equal to the center of the circle. You all agree? Look, the sigma that you have, so let's say this sigma here, I can write it in blue. This sigma is going to be equal to the center of the circle, isn't it? And the center of circle is equal to what? This is what? Alpha of sigma 1, very good. Which is equal to the radius of the circle, which is equal, so how much is this? How much is this? This is tau, right? Which is going to be equal to the radius of the circle, which, as you said, is going to be equal to sigma 1 over 2, right? Sigma 1 is the diameter, yeah? Sigma 1 is the diameter of this circle. If I divide by 2, I get the radius. So this is going to be equal, so look at this. This is the radius of the circle, isn't it? Yeah? So this shear stress is going to be equal to the radius, equal to sigma 1 over 2, equal to the center, if you want, of the circle. This sigma, so this is the sigma, right? This distance, yeah? Is going to be equal to the center, equal to sigma 1 over 2, equal to the radius, yeah? So we can say that this sigma here is going to be equal sigma 1 over 2. And this shear stress here is also going to be equal to sigma 1 over 2, isn't it? Yeah? You all agree with me? That's our conclusion here from the Mohr circle, right? So same thing for this point here in red. This direct stress is going to be equal to sigma 1 over 2. And this shear stress is also going to be equal to sigma 1 over 2. Yeah? So basically we did the stress transformation without doing any calculations, any mathematical operations, right? That's why I like the Mohr circle. You don't like, but I love Mohr circle. Because I can get everything from geometry. All these stress transformations, principal stresses, maximum shear stresses, maximum drag stress, everything comes from just this circle, right? From geometry, from the center, from the radius, yeah? Okay, so let's focus now on these stress components we have here. So we just need to calculate sigma 1, and then we unlock everything in this figure, right? Sigma 1. How do we get sigma 1? Well, we can go back. We can go back to this Mohr circle here we did initially. So this is the sigma 1 we are looking for. Yeah? So this sigma 1, I can say, is going to be equal to 2 times the radius of this Mohr circle in green color, right? But the radius of this Mohr circle, this is the radius, right, is equal to tau. Yeah? Which this tau is equal to is equal to the transverse shear force divided by the height of the web times the thickness. So I can say that this tau is going to be equal to the transverse shear force dividing by the height of the web times the thickness. So sigma 1 is going to be 2 times the transverse shear force times h over h times t, right? Yeah? So this is really the value I need to use here. Sigma 1 is going to be 2 times the radius equal to 2 times transverse shear force ht. Yeah? If I replace now this sigma 1 here, I will get, starting with this 1, sigma 1 over 2. So I will get here v over ht. And same thing in all other components, right? v over ht yeah? Okay? All right, any questions so far? Yeah?
You said earlier on about the convention was anti-clockwise positive, but you've swapped it, so the top red plane is positive.
Oh, yeah, you just reverse these arrows, yeah. Yeah, it's fine. Maybe this red point should be the blue one. Yeah, that's the thing. Yeah, but it doesn't matter too much. Yeah, okay. Okay, so more questions. So so far. So we're going to see now through one example how we can get everything now. The forces in the flanges, the forces in the stiffeners. Once the web buckles and all the load is being carried by tension in the diagonal direction of the web, okay? Because it's something, okay, so basically we are allowing the web to buckle. We are using a very thin web, right, to reduce weight in the aircraft. We are allowing basically the web to buckle, but we need to make sure that the flanges and the posts are able to carry the load. Because what is going to happen is the web will buckle, but then extra load is going to be on this direction, on the sigma 1 direction at 45 degrees, right? So the load that was being carried in this direction 2, after buckling, is not carried in that direction, but someone else needs to carry that load. So that load goes into this direction at 45 degrees in tension, right? So it means along this direction at 45 degrees is going to be overloaded, yeah? So we need to make sure then that this overloaded portion of the web transfers this load to the posts and to the flanges, and that the flanges and the posts are able then to carry that load. Yeah? That's why we need to calculate now the forces in the flanges and the posts. Okay? So I suggest we do a break, and then after that we do one example where we are going to calculate the forces in the flanges and in the posts in one example from beginning to end, okay? Following this theory, okay? Yeah? So, yeah, let's do a break then. So let's do this example here, I have here, which is basically a beam, well, a spar. It is clamped here. You have here the flanges, top flange and the lower flange. You have one stiffer here. You have post A and post B. So basically this is post B and this is post A. Okay? Now, you have 40 kilonewtons applied here, 40 kilonewtons, and you have 20 kilonewtons applied here. Now, dimensions for this, you have 300 millimeters, so dimensions are in millimeters, okay? From here to here is 400. From here to here another 400. And from here to here another 400, okay? Okay, good. Now, Catriva spar, equal spaced posts. Web thickness is constant, so the thickness is constant and equal to 1 millimeter. So you can see very thin, right? Very thin webs. And then they are saying here, the loading has resulted in a fully developed diagonal tension field throughout the spar. Okay? Now, plot the shear force and bending moment diagrams. Let's see if we can skip this one. Maybe we cannot skip this one. Well, I can skip this one in some way because I can give you the final shear force and bending moment diagrams. This is year one stuff, right? We don't want to repeat this. So, shear force and bending moments, you have for the shear force, you have Vx. So for this 0, x, and 40 degrees, you have Vx equal to 40 kilonewtons, and you have Mx equal to 40x kilonewton millimeters, right? And then for this region 400 x 1200, you get Px 60 kilonewtons, and you have Mx equal to 40x plus 20 x minus 400. Okay? So we can keep this. Let's not spend time in calculating again shear force and bending moment diagrams. Now, part B. They want to know the maximum compressive force in the flanges due to the combination of primary bending moment and the tension field effect. Okay, so basically they want you to calculate the forces in the flanges. All right. Maybe I can copy this. And paste it here. Okay, so we are going to define here a cutting section, right? And what we are going to have in this cutting section is we are going to have the forces in the flanges. We can put something like this. Force and in the top flange, and this is going to be the force in the bottom flange. We should represent these two forces in the opposite to each other, because it's the only way you can get the bending moment, right? And then what will we have as well? Well, we will have now I'm going to zoom in this bit here. We will have now this, so you need to keep this figure here in mind, okay? This plane stress element that was developed in the web due to the tension field effect, or due to the buckling of the web, okay? So because what I'm going to do now is I'm going to represent in red here several of these small elements. Yeah? See? So in all of these elements, so look, if you look at this face on the right side of each element of these elements, yeah, the equivalent face here is this one, right, in blue that you have here, right? Yeah? Can you see this? So what I'm saying is that if you compare this face here, so imagine this bit like if it is this plane stress element, right? So this face here on the right is equivalent to this face here, right? Where you will have a direct stress sigma and a shear stress tau. Yeah? So I can then say for each of these small elements I will have a direct stress sigma and a shear stress tau. Yeah? You remember when in year one, we said whenever you cut something with a section plane, right? You need to represent there the reactions or internal forces, right? That's what I'm doing. I'm cutting the web in this section. I need to represent there the internal forces, which are the direct stress sigma and the shear stress. So this is the shear stress tau, right, that you have. Yeah? And we know how much is this direct stress sigma and shear stress. So I can say this is the transverse shear force over the height times the thickness, right? Yeah? We obtained that before the break. You can see it here, right? Shear stress is also the transverse shear force over the height times the thickness. Yeah? So we have something like this. And now what we can do is we can, in fact, calculate now the we can calculate the moment about this bottom flange, about this point. I will call this point A, for example. What we can do is summation of moments about A needs to be equal to 0 to be in equilibrium. Yeah, our equilibrium equation for the moments. And then what we will get is, well, we have the moment produced by FB is 0. This force is passing on that point. The moment produced by FT, the force at the flange at the top, is going to be 300 times FT. You agree? Yeah? 300 FT. We have the moment produced now by, look, if you look at the shear stress tau, the shear stresses, they are passing on that point A, so the moment produced by the shear stresses is 0, right? But the moment produced by this sigma stress, direct stress, is not 0. Yeah? So you need to look at this sigma stress like if you have a distributed load on the web. Okay? So if you have a distributed load on the web, you have first the moment produced by these direct stresses that you have here about point A is going to be clockwise or anti-clockwise? Clockwise, right? So it's going to be negative, so I can say minus. Now this is a V over HT is what? This is my direct stress sigma. Yeah? So it's a stress. I need to multiply this by the area of the cross section to have a force, right? So stress times the area gives me a force, right? So which area is that? Well, this is 300 millimeters is the height. In fact, here I could have replaced the height and the thickness, right? The height is 300 and the thickness is 1, right? Yeah. So this is a stress. I need to multiply by the height again and by the thickness. So this is the area. Stress times the area gives me the force. So all of this is a force. Yeah. But I'm using the moment equation, right? So I need to multiply this force by a distance to get the moment, right? And that distance, you remember when we did in year 1 those beams with distributed loads? I said the force, equivalent force is located at the centroid. Yeah? So in this case, the equivalent force we can say is going to be located at this distance, which is going to be 300 over 2. Yeah? You all agree with me for the moment? So I need to multiply this now by 300 over 2. So if you want, this is the distance, and then the product of this force times the distance will give me the moment. So I can put this way if you want.
The thicknesses will be different in the divided by thickness, or if it's different to the...
Oh no, it's not different. Yeah, this T should be 1. Yeah. Yeah, all the thickness is equal to 1 for the webs, right?
Oh.
Yeah. Okay, so this is the contribution of the, basically, what is asking the question, calculate the maximum compressive forces of flanges due to the combination of primary bending moment and the tension field effect. So this is the contribution from the tension field effect. Yeah, this last bit we did. But we still have more moments about, point A, which are the moments produced by this 40 kilonewtons, yeah, and the moment produced by this 20 kilonewtons. Now, before we do that, in the question they are saying calculate the maximum compressive force. So we are cutting this section in a generic location X, we can say that like that, but the maximum bending moment, where do you think it is? In this beam here, if you look at this beam and with this distribution of this bending moment, where do you think it is the maximum bending moment? At the wall, right? Should be here, right? Yeah? So, because we are calculating the maximum, we need to, so this section here that we are using is going to be, so basically at the wall, right? So this distance from this 40 kilonewtons to here is going to be 1200, and from this 220 kilonewtons to here is going to be 800, okay? Yeah? You all agree with me? Because we want to get the maximum, yeah? So, let's start with this 40 kilonewtons. The moment produced by this 40 kilonewtons about point A is going to be clockwise, so minus 40 times the distance, which is 1200, and the moment produced by these 20 kilonewtons is going to be minus 20 times 800. Yeah? And these are all the moments we have. This should be equal to 0 to be in equilibrium. There is also one more thing we need to do in this equation, which is, so let me delete this. There is one more thing we need to do, is this V is a transverse shear force, which we need to have for the section at the wall, right? Which we have, right? You agree with me? Yeah? This is my transverse shear force. In this region here, so if you try to plot the transverse shear force diagrams in this figure, you will get 40 in this region, yeah? And in this region you will get 60, right? So at the wall, this is the transverse shear force that we need, 60, yeah? So I can, in fact, replace this V with 60 kilonewtons. And then, as you can see from this equation, the only unknown is the force in the top flange. It's quite easy, right? This comes from the summation of moments. And the result I have here is 243.3 kilonewtons. Quite a high force, isn't it? Yeah? You see? So one important thing is this term here comes from the contribution of the developed diagonal tension field, yeah, after buckling. While these two terms here, they come from the bending of the beam, right? Because of these two forces. So you can see that after the development of the diagonal tension field, this term here is adding more to the force in the top flange, isn't it? Yeah? So it means, due to the development of the buckling on the web, we are overloading the flange with more force, yeah? So we need to make sure the flange is able to carry that load without failing, okay? That's why we need to calculate the force in the flange. Now, force in the bottom flange you can obtain from, for example, summation of forces in the x direction equal to 0. Yeah? Then the only unknown will be Fb. Or if you want, you can also calculate the moments about this point. Let's say this is point B, for example. Yeah? And then you get Fb from that equation as well. Yeah? So you can calculate the force in the bottom flange by using any of these two equations, right? Okay? Everything comes from equilibrium again, yeah? This is something I told you in year 1, right? Everything is in equilibrium, you can see. Everything always in equilibrium. Right, so part C is they ask you to calculate the forces in post A and post B. Now we need to calculate the forces in the two posts. So let's start with post A. So maybe I can use a new one. So we have, let me draw here again our beam. Yeah. So this is post A. This is post B. So what I'm going to do is, the first thing you need to consider is, okay, we have here basically 3 posts, right? The one at the tip, post A and post B. So what we are going to say is, we are going to say this post here at the tip will get the contribution. So if I divide this distance by half, so look, if I take this, if I do the free body diagram of this bit, I will have something like this. I will have this little bit of the flange. Yeah. And I will have here my post at the tip. And then I have this part of the web. But for this part of the web, we need to go back here again. So what I'm going to do is, I'm going to represent here in red these small elements. Okay? And now look at this. I need to look at these faces of these elements and compare with this figure. And those faces, they are equivalent to this shear plane here, right? Yeah? Maybe I can use the black color. This shear plane here in black will have the direct stress, which is again equal to V over HT, right? And it will have that shear stress, right? So this plane here at the bottom, keep that in your mind, because it is going to be that same plane here at the bottom with a direct stress which is equal to V over HT, yeah? And also with a shear stress which is going to be equal to V over HT, but that shear stress, we are not going to bother too much with it because we are going to do the equilibrium in the vertical direction. And we have something more else. So imagine I am doing, like you did in year 1, I'm cutting. So this thing here, it means I am cutting part of my spar, this part inside this box, and I'm analyzing that. So what did I cut? Well, I did cut the web here, and I did cut the post as well, right? So before I cut the post, I need to include a force in the post. F, force in the post, FP. And I'm assuming that force in the post is going to be compressive. Yeah? Okay? If I do the same analysis for post A, so I will have to, I'm going to use now the green color. I will have to cut this part of my spar inside this green box, yeah? And then I do a similar analysis for this one, which will give me something like this. I will have part of the flange, post here, and then I will have these small elements. Let's make only 2 is enough. Where these elements will have this direct stress sigma V over HT. Same for these two, right? Sigma equal to V over HT. And then I will have the force in my post A. Let's say F post A. Another free body diagram, like we did in year 1, right? We did many free body diagrams, remember? Same thing here. So this is a free body diagram for post A. And from the equilibrium of the forces in the vertical direction, I will get force at post A. Yeah? And then I can do the same for post B. Okay? Now there's only one more thing we need to consider before we do the analysis is we need to get these distances. I need to get this distance from here to here for the post at the tip. I need to get this distance from here to here from post A and also from here to here. And same thing for post B. I need to get those distances. So what I'm going to assume here, and is a reasonable assumption, is, look, what you have here in red, this is because of the development of the diagonal tension field, right? Yeah? So when the web buckles, this sigma direct stress is developed and are going to be transferred to the posts as well. Not only to the flanges, but also to the posts. And then what I'm going to say is that if I look at this web here, maybe I can shade this web like this. If I look at this web, what I'm going to say is that half of that developed diagonal tension field is going to the post at the tip of the spar, and the other half is going to post A. Yeah? So in that case, I will say that this dimension here is going to be 400 over 2. Same thing for this one, 400 over 2. Yeah? Make sense? Now, if I look at post B, this one here, this is post B, I'm going to say also the same thing. So half of the developed diagonal tension field from this web at the center is going to post B, and half is going to post A. So in that case, this dimension from here to here is going to be also 400 over 2. Yeah? And this one from here to here, also 400 over 2. Okay? So it means for post A, this is going to be 400 over 2. Yeah? And why do we need these dimensions? Because, okay, let's do now the equilibrium for post A. So for post A, we are going to do summation of forces in the vertical direction equal to 0. We get the force at post A, F post A. It is already a force. Now we have minus the contribution on this side, this left side of the post, which is going to be the stress, which is V over HT. I'm going to write like this and then we can replace. So this is a stress. I need to multiply this by an area to get the force. Which area is that? Well, I need this 400 over 2. That's why I need this. So times 400 over 2. And I need to multiply now by the thickness, which is 1 millimeter. Huh? So this is the contribution from the diagonal tension field developed on the left side of post A. I need also to add the contribution from the diagonal tension field developed on the right side. So maybe I can do something like this. V on the left side and V on the right side of the post. Okay? Just to distinguish between these two. HT times, again, distance 400 over 2 times the thickness. And this should be equal to 0 to be in equilibrium. Okay? So I can replace this HT because the height is always 300 and the thickness is always 1. So 300 times 1. Yeah, same thing here. And now I just need to get the force, the shear force at the left of the post and at the right of the post, but we have that here, right? So at the left side of the post, in this region, the transverse shear force is 40, yeah? While on the right side of the post, the transverse shear force is 60, okay? So this comes from the transverse shear force there. So this is one application of the transverse shear force diagrams you do in year one. You did in year one, right? One application, for example, on the Spar theory. So 40 kilonewtons here and 60 kilonewtons here, okay? So the only unknown in this equation is the force in the post A, which according to my calculations here according to my calculations here, you get something like 66.7 kilonewtons. Okay? For post B, we can do maybe summation of forces in y direction equal to 0 again. So you have the force in post B. So it's very similar with this one. The only difference is here you don't have force in post A, but you will have force in post B. Even these dimensions, 400 over 2, 400 over 2 are the same, are the same dimensions, right? You just need to be careful with the with the transverse shear force on the left side of the post and transverse shear force on the right side of the post. Yeah? So we can basically write a very similar equation that the one we wrote for post A. Now, force for post B, look, the transverse shear force on the left and the right side of post B, they are equal to 60 kilonewtons, right? Yeah? So we'll have what? 60 kilonewtons here over 300 times 1 times 400 over 2 times 1. This is the same. But now here again, minus 60. 1 times 4. So it's exactly the same as what we did for post A, right? So post B is going to be more overloaded than post A. And the result I have here for post B, I cannot scroll down anymore. So I'm going to put it here. The result I have there is 80 kilonewtons. 80 kilonewtons for post B, 66.7 kilonewtons for the force at post A. Okay? I will try to find, because I think there are videos showing this, the development of the diagonal tension field in a spar. You can see the, like I said here, in this step from here to here, right? I told you that the web is going to buckle in this direction too. So I'm going to try to find some videos to show you next week where you can see the web buckling in this direction, number 2, okay? This diagonal tension field developing in aircraft. Yeah? Okay, so this is the Spar. So it's an important thing in aircraft structural design. Basically, we allow the spar to buckle, or the web of the spar to buckle, but it's a controlled buckling, if you want to call it that way, okay? Because we then calculate the forces in the flanges, in the posts, the tension, the stresses are on the web, and we make sure that all these different structural components are able to carry that overload these components are getting, okay? So we could do more examples, but this is it, yeah? So only the dimensions and geometry will change, the loads might change, but this is all about this now, yeah? So we might, because of your project proposals, yes?
So can you go back to the last slide and pick up it?
Last slide. I will upload the video, right? So, yeah, because I know you guys are in a rush, you have a deadline tomorrow, project proposals, and I'm really tired today. Maybe we get the 15 minutes bonus, okay? Yeah? Only this week, next week. All right?